Okay, so another calculator particle motion problem. Given a velocity equation for the particle moving along the x-axis. Also, we're given an initial position that is x equals -5 when t equals 0. We want to find the acceleration at time t equals 3. So all we have to do is figure out what the derivative of the velocity is at 3. And because this is a calculator question, you will literally just use the function on your calculator. You'll write v prime of 3 equals, and then you'll use your calculator to approximate this. And it should come out to be -2.118. And that is it for part A. A whole amazing 1 point there. Good or no?
Good.
Perfect. That should have been easy. All right, part B. So let's find the position of the particle at t equals 3. Well, the position of the particle ought to be whatever its displacement is from 0 to 3 added to its initial position. So its initial position, x of 0, plus the displacement from 0 to 3 of the particle. That should be its new position. X of 0 was -5, and your calculator will integrate for you the value of the integral from 0 to 3 of that. I guess we'll write -5. -5 plus, I don't know, what does that integral come out to be?
3.240.
3.240 something.
Yeah, that's just rounded.
Yeah. So then that looks like that should be -1.760 is its position at t equals 3. And that may seem really easy. Hopefully that seems really easy, but that's worth 3 points. 1 point for having the correct integral, 1 point for remembering to use the initial condition, and 1 point for getting the correct answer. Right. So you got to remember that the integral from 0 to 3 of v of t gives us the displacement in those 3 seconds time. There's no time period in those 3 units of time. So we have to add to it where it was at 0 to see where it is at 3. Good or no? Okay. So then we'll evaluate the integral from 0 to 3.5 of v of t. Well, that should be easy. All we have to do is plug that into our calculator. So that should have come out to be 2.844. And the explanation of what that is should be the displacement of the particle from t equals 0 to t equals 3.5. That's really all you would need to write for that. And then the second part of it, this one, when you took the absolute value of this and integrated it from 0 to 3.5, that should have come out to be 3.737. And you would have said that this is the total distance traveled. By the particle on that same interval, time interval. Easy enough there, hopefully.
Yep.
Yeah. And you got 1 point for the values. And you got 2 points for the explanations. Okay. Everybody's good there?
Yeah.
All right. Part D then says we got a second particle moving along the x-axis. It's got a position equation that we got. t squared minus t for 0 to 3.5. We want to know when are the two particles moving with the same velocity. So all we need to do is, first off, find the velocity function of this. So we'll say for part D, we got v sub 2 of t should just be 2t minus 1. And if we want to know when that velocity is equal to this velocity, we'll just set that equal to 10 sine of 0.4 t squared over t squared minus t plus 3. And your graphing calculator will tell you where those two functions intersect on the interval between 0 and 3.5. And it appears that was 1.571. And 2 points for that. 1 for the equation and 1 for the point. Any questions on that?
Nope.
All right. Everybody feel okay about the first couple of particle motion problems we've dealt with? I hope. Okay, so this is our first non-calculator one. So we got two particles moving along the x-axis. We got particle P, and we're given its position. And then we got particle Q, and we're given its velocity. And then we're given an initial position for particle Q. Okay, so the first thing we're trying to find is for the time interval from 0 to 8, we want to know when is particle P moving to the left. Well, particle P will move to the left if the velocity sub P, the velocity of P, is less than 0. Well, we don't have a velocity function for particle P, so we need to find P sub D, which should be the derivative of the position of particle P, which should be the derivative of natural log of t squared minus 2t plus 10, which is just 1 over t squared minus 2t plus 10 times the derivative of t squared minus 2t plus 10, which is 2t minus 2. And we want to know when is this thing less than 0. So on the interval between 0 and 8. So first off, the times when it might change from being greater than 0 to less than 0 is when it's equal to 0 or when it might be undefined. So we'll go in and say 2t minus 2 equals 0 gives us t equals 1. So that's one possibility. And then we look at this one down here too. Anything that makes this undefined. So if we tried to figure out when that's undefined, we'd find out that we can't factor that. And then we try to use either completing the square or the quadratic formula, and you'd find that the solutions to t squared minus 2t plus 10 are imaginary. There are no real solutions to that, which you can figure out by doing the discriminant, right? Negative 2 squared, b squared minus 4 times 1 times 10 is negative, so there's no real solution. So the only things we're looking at here are between 0 and 1 and 1 to 8. And so if we plugged in something that was between 0 and 1, like a half, well, we know this is going to be positive. So this is always positive. And this, if we plug in a half, is 1 minus 2. That's negative. So our velocity is negative from 0 to 1. Then we'll check between 1 and 8 to make sure it actually does change signs. So plug in something like 5. The numerator is positive and the denominator is positive. So moving to the right. And so we would say that this particle is moving to the left for t equals 0 to t equals 1. And that part was worth just 2 points, 1 for correctly getting the derivative and 1 for having the correct interval. Any questions there on part A?
Is that interval inclusive or?
So we would, let's see here. We wouldn't include it at 1 for sure, because we know that the velocity is 0 at t equals 1. For less than 0, I mean, sorry, for less than 1, but greater than, would it be greater than or equal to 0? Yeah, you could include it there because technically to the left of 0, it would be inclusive. So you'd want to say t is greater than or equal to 0, less than 1. Generally, though, in these motion problems, they're generally less concerned about the endpoints. That doesn't mean that you shouldn't be careful about them. But if you were to write from t equals 0 to t equals 1, they would give you the points for it also. So you don't actually have to write it in an interval or a set notation. All right, for part B, we want to find all times during which the two particles travel in the same direction. So we know which direction particle P is traveling in from 0 to 1 and from 1 to 8. We need to figure out now about particle Q. So particle Q had a velocity of, what was it? T squared minus 8t plus 15. And so we can figure out when that's positive and when that's negative by factoring it. T minus 5, t minus 3, and we then make a chart here with 0, 3, 5, and 8 and test values. So between 0 and 3, it's something like 1. This is a negative times a negative, which is positive. Between 3 and 5, something like 4, it's a negative and a positive. So that's negative, and 5 and 8, something like 7, it's a positive and a positive. And so if we were to look at the chart that we had, this is for Q. If we were to look at the chart that we had for P, the chart we had for P had 0, 1, 8, and we had negative and positive. Is that right? Yeah. So, well, when are they moving the same direction? Well, from 0 to 1, they're not, right? But from 1 to 3, they certainly are. And then again from t equals 5 to t equals 8.
And again, would you say it's only like reasonable to put that or equals to when you're concerning the 8?
Yeah, so the only one that you'd want to do that for would be the 8, yeah. So if you were to write it, you do 1, 3 union 5, 8, or you could do t is less than 3, greater than 1, less than or equal to 8, greater than 5. Yep.
If we
And that
didn't
one,
do it exactly like that, where we had like not less than or equal to, but just like less than, would we still get the point?
like I said, I think generally they're okay with you having these off on like the velocity problems, but just be careful about it. I mean, it's better to have it more accurate, but this answer is also fine. So if you're concerned about it, about making a mistake, you can write it out in words and they will accept that.
Okay.
So then there's no need to worry about it. Nothing in the scoring guidelines says they accept this, but I've seen like tons of instances because they give us like student sample work to look at also. It's like I've seen tons of instances where kids just write it out like this and they give them the points. So this one was worth just 2 points as well. 1 for having the correct intervals and 1 for some sort of analysis to show that it was correct. All right, next part was part C. Part C said find the acceleration of particle q at time t. So we'll start with that. The acceleration of q, so a sub q, ought to be v sub q prime. And now I've forgotten what v sub q was. Looks like it was t squared minus 8t plus 15. So that'll be 2t minus 8. And we wanted to find what a sub q of 2. Yeah. So we'll evaluate this at t equals 2, which gives us negative 4. So we got an acceleration of negative 4. And then the second part of that question said, is the speed of q increasing, decreasing, or neither at time t equals 2? So we talked about this some point on a problem fairly recently in the multiple choice. Remember that speed increases if velocity and acceleration have the same sign. And speed will decrease if velocity and acceleration have opposite signs. So we know that at t equals 2, the acceleration is negative. And if we go back here at t equals 2, we're talking about q, the velocity is positive. So we would then say v sub q of 2 is positive, a sub q of 2 is negative. We would say that the speed is decreasing. And you'd want to say because acceleration and velocity have opposite signs. And that was, again, worth 2 points. 1 point for the value and 1 point for decreasing with an explanation.
So if we totally blanked on the fact that they were saying speed and not velocity and just gave like the typical explanation of like the derivative was negative, therefore it's decreasing, would we not get the point?
You would not get the point.
Okay.
Yep, because your explanation is wrong. Yep. Yeah, so be very careful about the words speed and velocity. They will ask about both things in these motion problems or in some of the multiple choice. So just be careful about that. All right, and then the last part of this one, part D, says we want to find the position of particle Q the first time that it changes direction. So the position of Q the first time it changes direction. So we need to find the first time it changes direction. First time particle Q changes directions is at t equals 3. Right? So we're going to say we want the position of Q at t equals 3, which should be the initial position of particle Q plus the displacement from 0 to 3, which our displacement should be the integral of our velocity function. Everybody good with that as the setup? And our velocity function was t squared minus 8t plus 15, and our initial position was 5. So this becomes 5 plus the integral of from 0 to 3 of t squared minus 8t plus 15, which should be 5 plus t cubed over 3 minus 4t squared plus 15t from 0 to 3, which should be 5 plus, this will be 9 minus 36 plus 45, and then minus 0. So whatever that comes out to be, what is that? 9 let's see, 9 minus 36 ought to be negative 27 plus 45 ought to be 18 plus 5 ought to be 23. And that was worth 3 points, 1 for having the correct antiderivative, 1 for using the initial condition, and 1 for the final answer. Any questions on any of that problem? All right, let's look at the next one. I still had you guys do this one already, right?
Yeah.
All right, so we're looking at the calculator one. We want to know at time t equals 4, is the particle speeding up or is the particle slowing down? So basically, is speed positive or is speed negative? So this is, again, speed, which means we need to look and see if the velocity and the acceleration have the same signs, or if velocity and acceleration have different signs. And so we'll first find v of 4. So v of 4 using your calculator should come out to be 2.9 something, 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 78, something, clearly positive. And then you'd use your calculator to evaluate the derivative, so the acceleration at 4. And that comes out to be negative 1 point something, 1640 something, which is less than 0. And so we would say it is slowing down. And you'd want to give a reason for that slowing down, because v of 4 and a of 4 have opposite signs. And that was worth 2 points. For you basically had to have all of that there. You had to figure out the right values, show that one was positive, one was negative, and say that it was slowing down because of the opposite signs. Any questions there on part A? Okay. Part B. So for part B, we want to know on the interval 0 to 3 when the particle changes directions. And so in order to figure out places where it might change directions, you'd take 1 plus 2 sine t squared over 2 and set it equal to 0. And you'd find a t value of 2.70748. And you'd want to either do a sign chart to show that it changed signs, that it went from positive to negative, which you could see by looking at the graph. So those arrows in there, but you'd have the graph sitting in front of you, right? If you had your graphing calculator, and you'd want to, either make the sign chart and show that, or you'd want to make a statement that says the derivative goes from positive to negative. And so, just to real quickly look at this here, we got it was 1 plus 2 sine of t squared over 2, I think, right? And so there's your value of 2.707. It's the only one between 0 and 3, because 3.394 is greater. This is the derivative, or this is your velocity function, right? So the velocity goes from positive to negative, which means it had to change directions. It went from moving to the right to moving to the left. Good or no?
Good.
1 point for the number, 1 point for the justification, either a sentence that said that v changed from positive to negative, or a sign chart that shows that that's what you had. that. And always make sure you indicate what your sign chart is showing. All right, part C. Part C asks us to find the position of the particle at time t equals 0. And so in order to figure out that position, we need to take an initial position that we had. We were given a position of 2 when t was 4. So we should just take 2 plus the integral from 4 to 0 of v of t dt. And if you prefer to write this the other way around, you can flip the limits if you want, but it doesn't really matter. And then your calculator will just evaluate that for you. Comes out to be negative 3.815. And that was worth 3 points, 1 for having the right integral set up, 1 for the initial condition, and 1 for the answer. Any questions there on part C?
Nope.
All right, so for part D, we want to find the total distance the particle travels from t equals 0 to t equals 3. So total distance should just be the integral of the speed, or in this case, an integral from 0 to 3 of the absolute value of our velocity function. And since we have a velocity function given to us, we can just integrate the absolute value of it, and our calculator will give us that value as 5.301. 1 point for the answer, 1 point for the right integral setup. Pretty straightforward.
Yeah.
All right. Let's take a look at the next one. This is the last one I think I had you guys do already. Is that right?
Yeah.
Okay. So this one, we've got a chart given to us, a little bit different. We got a person jogging on a straight path, and we just got values of her velocity in meters per minute at different times. Clearly, it looks like she went on the straight path for a while, then turned around and went to the left again, and then went back to the right at some point. So first thing it wants us to do is to use the data in the table to estimate the value of v prime of 16. So to find the derivative of v, the easiest way to do that will just be to approximate it using the average rate of change, finding the slope between 12 and 20, because those surround 16 pretty nicely there. So we will say v prime of 16 is approximately equal to 240 minus 200 over 20 minus 12, which will give us 5 meters per minute squared. And if it asked us, what that was, that would be, an approximation for her acceleration at that time. But it doesn't, and that was just worth 1 point there. Any questions there on part A? That's a pretty common thing that they'll ask you to do, is approximate, given a chart, the derivative of the function that's shown in the chart. All right, part B says, using correct units, explain the meaning of the definite integral from 0 to 40 of the absolute value of v of t. So the meaning of that should be, since this is the absolute value of velocity, that's speed, and when you integrate speed, you get a total distance traveled. So we would say something to the effect of it's the total distance that she runs or jogs or whatever from t equals 0 to t equals 40. So that'd be your explanation for what that means. And then it says it wants us to approximate that value using a right Riemann sum with the 4 subintervals from the table. So approximating that with our right Riemann sum, let's see, first off, this is 1 point for the explanation. So our right Riemann sum should be the y value here, 150, times the length of that subinterval, which is 24 to 40, so that'd be 16, plus the next height, which since we're doing the absolute value, that's going to become a positive 220, times the length of that subinterval, which is 4. Then the next one, which will be 240, times the length of that subinterval, which was 8. And then the last one will be 200 times the length of that subinterval, which is 12. And you just add up all of those things, and it should come out to be, let's see here, 16 times 150 ought to be 2,400. That's 880. Looks like that comes out to be 7,600 meters. Any questions there on part B? So 1 point for setting up the sum correctly, 1 point for getting the right sum, and then 1 point for that explanation earlier in that problem. Everybody good with part B? Cool. Then we've got part C. Part C says Bob is riding his bicycle along the same path. And from t equals 0 to t equals 10, his velocity is this equation. And we want to find his acceleration at time t equals 5. Well, an acceleration should be a derivative of our velocity. So we'll say b prime of 5. So we're just looking for b prime to start with, which was 3t squared minus 12t. And at t equals 5, that ought to be 75 minus 60. So that would be 15. And what were our units? They were meters per minute. So acceleration would be meters per minute squared. Good or no? Any questions there? Part C. 1 point for finding the derivative, 1 point for the right answer with the units.
I have a question about part B. Could you just go back one real quick?
Sure.
So on the 220, I put negative 220 since that's what it says in the table. Are we not supposed to do that?
Absolute value.
Oh, crap. Okay.
You approximate the value of the absolute value of that. So. All right. So then for part D, we want to find his average velocity, and an average of a continuous function that we're given here, t cubed minus 6t squared plus 300, ought to be the mean value theorem for integrals. So part D, this is part C. Part D ought to be the 1 over b minus a times the integral from a to b of his velocity function, which was what? T cubed minus 6t squared plus 300. And so we will evaluate this integral. Got 1/10 of t to the 4th over 4 minus 2t cubed plus 300 t. And we'll do that from 0 to 10. So now we've got 1/10 of, let's see, 10,000 over 4, that's 2,500. Minus, that should be minus 2,000. And then that should be plus 3,000, and then minus a bunch of zeros. So we've now got 3,500 over 10, which ought to be 350. And if it's in velocity, it should be meters per minute. Any questions there on part D? 3 points for that one, 1 for setting up with the correct integral, 1 for having the correct antiderivative, and 1 for getting the right answer in the end. Good or no? Any questions on that?
Yeah. The equation given, wasn't that like already the velocity equation? So integrating it would get like a position function.
Yeah, integrating gives you the position function, that's true. But this is a function that represents velocity. It asked us for the average velocity, and the mean value theorem for integrals says to find the average of this function, which this function represents velocity, so it's the average velocity, is 1 over b minus a times this integral. Effectively, what you've done is you found, his displacement over that entire time interval from 0 to 10, and then divided it by the 10 minutes that he was bicycling. So this, the integral itself, is a representation of meters, but this is you dividing by the number of minutes that he went those meters.
Okay.
Does that make sense?
Yeah.
Cool. All right. I believe that's the last one I had you guys do in advance. Is that correct?
Yeah.
All right. So here is a problem about a train, which is relatively similar to the one we were just doing. So I'll give you guys 15 minutes to work through this one, and then we will go through it. Hopefully we'll have time to go through it today. And then I'll assign a couple more for Monday. We're not going to take the quiz on Monday. And I think the next multiple choice section is Tuesday. Is that right? Or is it Wednesday?
I thought it was Wednesday. Let me check.
Wednesday? Okay.
It might be around that. It might be wrong. It's on the 16th.
That's Tuesday. Okay, so we will plan on having the quiz on particle motion on Wednesday, the 17th. So we'll spend Monday going over a few more. Tuesday we'll do the multiple choice. Wednesday we'll do the quiz on particle motion. So I'm going to give you guys 15 minutes right now to work through this one, and then we'll talk about it, and that'll be that. So ready, go. So for the train problem here, we've got train A that's got its velocity there in the chart, and we want to find the average acceleration of the train over the interval from 2 to 8. So if we're looking for the average acceleration, that ought to be a change in the velocity with respect to a change in the time. So we'll just do that from 8 to 2. So that should give us negative 120 at 8 minus 100 at 2 over 8 minus 2, which should come out to be, what is that, negative 220 over 6, so negative 110 over 3 meters per minute squared. And that's 1 point. So just like the last one. Everybody good there with part A?
Yeah.
All right. Part B asks us, does the table support the conclusion that train A's velocity is negative 100 meters per minute at some point between T and A? So the answer to that should be yes, because we know that this is a differentiable function, and if the function is differentiable, that means that the function is continuous. So we know V of A is continuous. And because it's continuous, and between 5 and 8, we go from 40 to negative 120. The intermediate value theorem says V of C must equal negative 100 on the interval from 5 to 8, because negative 100 is on the interval between 40 and negative 120. Does that make sense to everybody for part B?
I thought you had to use the mean value theorem for things like this, because I know we had a problem a couple ones back where we used like the mean value theorem instead of the intermediate value theorem on a similar type problem.
That one was probably asking something different. I believe that I sort of remember the one you were talking about. In fact, was it the particle one?
I don't remember the specific.
Yeah, this one was, so if we go back and look real quick, the difference between this one and that one is we had velocity here, and it said justify why there must be a time where the acceleration is equal to 0. And so we use the mean value theorem because the acceleration is the derivative of velocity.
Oh, okay.
But here it asks us to justify why the velocity is negative 100 given a bunch of velocity. So there's no derivative involved.
Oh, I see.
There's no
So
mean
it's
value.
the same. Oh, I see. Okay, okay. So the units were different, or I see. Yeah.
The thing we were trying to show was velocity here rather than acceleration there, both given values of velocity. So that's why. Does that make sense now?
Yeah.
Okay. All right. Part C says at time t equals 2, we've got train A's position is 300 meters east of the origin station. Wow, that's a great name for a station. And it is moving to the east. So we want to write an expression involving an interval that gives the position of the train at t equals 12, and then we're going to use the trapezoidal sum to approximate that. So first off, if we know where it is at t equals, what do we know, t equals 2, then we're going to need to integrate from 2 to 12 of that velocity. How did they write it? They wrote v sub a, right? V sub a of t dt. But we have to include the 300 from the initial position at t equals 2. Everybody good with that being the basic initial setup?
Yeah, I got that, but I'm just curious why we couldn't have just done an integral from 0 to 12 and just ignored the initial 300.
Well, because it doesn't tell us where the train is at 0. It doesn't tell us if it's starting at the station or if it started east of the station or west of the station, or there's no indication of where it is in comparison to the origin.
Okay.
So you have to use the initial condition that they give you. You can't just make up one of your own. So that's why. So this is our initial setup. That's worth 1 point for having all of the setup there, right? And then you need to do your trapezoidal sum. So we're going to do 300 plus, and then our trapezoidal sum from 2 to 12 should look like the first base plus the second base. That's 100 plus 40 over 2 times the length of that interval, which is 3. So 100 plus 40 over 2 times 3. The next one should be 40 minus 120 over 2, also times 3. And the last one, which is the one that made it so that we couldn't use just the formula for the trapezoidal rule, has a length of 4. So that should be negative 120 minus 150 over 2 times 4. And you got 1 point for correctly setting up the trapezoidal sum. And then 1 point for properly evaluating it. I'm not going to go through all of the arithmetic there. That ended up coming out to be negative 150. And so we would, I don't know if it, what did it say? To approximate the position. So yeah, we'd say it's at negative 150, or you say it's 150 meters west of, I'm not going to write origin station, so I'm just going to say west of the station, because I just can't do that. Any questions there on the rest of part C?
What was
1
the
point.
breakdown for part B?
Say that again?
What was the point breakdown for part B?
1 point for 1 point for showing that negative 100 was between 40 and negative 120, and 1 point for saying intermediate value theorem and having some explanation using the intermediate value theorem.
Okay.
All right, and last part of this one, part D, says we got a second train traveling north from origin station. At time t, the velocity of train B is given by this, and at time 2, it's 400 meters north of the station. Find the rate in meters per minute, which the distance between train A and train B is changing at t equals 2. So we've got train A is moving along this axis, train B is moving along this axis. The distance between them, we'll call this x, and we'll call this y, right? Ought to be z, and those could be related using x squared plus y squared equals z squared. And so this is going to be a related rate problem where 2x dx dt plus 2y dy dt equals 2z dz dt. And we're interested in all of these things when t equals 2. So if we go back here, at t equals 2, train A is 300 meters east, so x equals 300. Train B is 400 meters north, so y will be 400. And I think using a little bit of simple right triangle trig that you probably don't even need to write out, z would then be 500. Right, just the 3, 4, 5 right triangle. And then our value for dy dt should be this velocity equation right here, evaluated at 2. So we'll find out v, so dy dt equals v sub b of 2, which was, now I have it in front of me. At 2, that'll be negative 20 plus 120 plus 25. Oops, negative 20 plus 120 plus 25. So that ought to be 125. And then our dx dt, which is the velocity of train A at 2, we should be able to just find that one from the chart. That one should just be 100. And we'll just plug everything in. So 2 times 300 times 100 plus 2 times 400 times our dy dt, which was 125, equals 2 times 500 times what we're looking for. And divide everything by 2 if we want and get rid of all those. Divide everything by 100. Get rid of all of that. And that'll make our arithmetic a little bit easier here. We got what? 300 plus 600, that's 900 divided by, what is it? No, that's 500. 300 plus 500, so 800 divided by 5, which ought to be dz dt equals 160 meters per minute. Any questions there on that nice little related rate problem that got thrown in? 3 points. 1 for having, 2 for having this, and 1 for having your final answer. Everyone good there with part D? Any questions?
Wait, what was the point breakdown? 1 for the answer and 1 for the setup?
2 points. 2 points for having for correctly implicitly differentiating x squared plus y squared equals z squared with respect to t. 1 point for 160 meters per minute.
Okay, thanks.